Isaac Newton had a problem, and the problem involved the distance versus time graphs of moving objects. So here we have a distance versus time graph, and let's say the red line represents the distance versus time graph of a red car, and the blue line represents the distance versus time graph of a blue car. So Isaac Newton knew that the slope on a distance versus time graph represents the speed of the object. So the good thing is you can just look at this graph and instantly know that this red car is traveling faster than the blue car because the red line is steeper than the blue line. In fact, if you wanted to calculate the actual slope mathematically and you knew the distance here in miles and you knew the time here in hours, for instance, to calculate the slope you just take the rise divided by the run. So you get miles here divided by hours here. You get miles per hour, and that would be the speed of the car. And it's not just because red cars are faster than blue cars, it's because this line actually has a steeper slope than this line. You can just look at it and see. Now, I'm not saying that automobiles existed in Isaac Newton's time. Probably they didn't. But I am saying that an important thing about a distance versus time graph is that the slope of the graph equals the speed of a moving object. Now that's not the problem. The problem is calculating the slope of a line to find the speed of the moving object only works if you have a straight line graph. Now, what Isaac Newton's problem is, what if the object has a changing speed? In other words, the slope of the line is going to be changing as time goes on. So here's an example of a moving object whose speed is changing. And let's say it's a blue car, and you can just by looking at it see that, well, here the slope's not very steep, and so we can know, in fact, right here, looks like the slope, it might be a horizontal line right in here, so the slope of a horizontal line is 0, so we know right here the speed of this object is 0. Now as time goes on, as time goes to the right, notice the slope gets a little steeper, slope gets a little steeper, so the slope is increasing, so the speed of the car is increasing. Notice that so here's an object starts out at 0 velocity and the slope gets steeper and steeper and steeper. Here it's really steep and it's going pretty fast relatively. So if you're having trouble looking at a graph and deciding on steepness, what you can imagine is, what if you were a skier here? If you were a skier right there at that slope, that'd be a crazy steep slope. That'd be a triple black diamond slope. And the same notion that you have about skiing down slopes, that applies to graphs too. So here, that's really steep, but if you were skiing here, that would be the bunny hill. That's not steep at all. And so you can use your skiing intuition to figure out distance versus time graphs, where there's things as at that instance, is it really steep? That means it's really fast here. If it's not very steep, it's not going, relatively, it's not going that fast. So it's just like, here's the triple black diamond, and that's really steep. This is the bunny hill. That's not very steep. So there's a couple things I want to point out. Is one, this whole line here no longer has just a single slope. There's not a single number. We can't say the slope of this line is 35 miles an hour, because notice, the slope of this line at any given point is going to be a different number. Right? So for changing speed, we need a new piece of vocabulary, and it's called the instantaneous speed. So if we have an object with changing velocity, now if we want to talk about changing speed, I should say, actually, there's a slight subtle distinction between velocity and speed that I'll talk about later. But we now have to say, we can only say the speed of this car, let's say right at this, let's say right here on this time axis, that's 4 seconds. We can say the speed of this car right at 4 seconds is its instantaneous speed. Because notice, like let's say maybe here this is 2 seconds, right here the time. Let's say, for example, this is 2 seconds. We can say the instantaneous speed right at 2 seconds is maybe 15 miles an hour, I don't know. But notice, we can no longer give one number for speed, and so now we have to specify instantaneous speed. That means at any given instant in time, what is the speed right there? So prior to Isaac Newton inventing calculus, if you wanted to know an object's instantaneous speed, what you would have to do is you'd actually have to take a ruler, you have to have your graph, you have to take a ruler and you'd have to draw a tangent line to the graph. Now, a tangent line is a line that touches the graph only at a single point. Let's say right there. That's too much. Let's say right. It's hard to draw tangent lines, and this is why Isaac Newton was dissatisfied. So let's say that's approximately that red line touches my graph right there at a single point, right? And so let's say for instance that was 4 seconds. So if I wanted to find the instantaneous velocity right here at time equals 4 seconds, I'd have to draw a tangent line that touched the graph right at x equal, or the time index equals 4 seconds. And I'd have to take a ruler, draw the line, then from the graph I'd have to calculate the rise of the straight line that I drew, and I'd have to find the time interval of that straight line and divide the rise over the run, and that would be the slope, and that rise over run of this straight line, of this tangent line, would tell me the instantaneous velocity right there, right at 4 seconds. And notice if I wanted to have to find the velocity of the blue car at any other time, then I'd have to draw another line, and let's say I wanted to find the velocity right there at, let's say that's 2 seconds. So that's not quite touching. Let me see if okay, there. So right there at 2 seconds, and so right here, let's say for instance that right there was 2 seconds. Right there was 2 seconds. Then I'd have to find the rise over the run of this other line. So notice, to find the instantaneous velocity of a car whose speed is changing is a lot of work. And it's not very precise, because remember, I'm just eyeballing this line. So I just look, I try to draw a line that touches the tangent line that touches my graph right there, right at 4 seconds. And I try to draw a line right here that just barely touches a single point right at 2 seconds, say. And then I have to actually read off the graph how high this rise is. I have to notice it's going to be kind of hard to read off this graph for that tangent line. If I get the run here, whatever that is in hours, and whatever the rise is in miles, say, I have to read after the graph, then I have to divide the rise divided by the run to get the speed. It's a lot of work, and notice that would only tell me the speed right there at that instant in time, and the speed right there at that instant in time. And on top of that, it's not very precise. So you can see why Isaac Newton is kind of dissatisfied with this method. What Isaac Newton wants to do is develop a mathematical method for calculating the slope of a tangent line. So the problem is, how we did it before Isaac Newton is we just had to look at it and sort of guess, okay, that looks like it's a tangent, then we calculate that slope. But what Isaac Newton wants is he wants a mathematical method, and he wants it to be exact and not just guessing. So here's what he does. He says, I don't know how to calculate the slope of a tangent line, but what I can calculate is the slope of this chord. So notice it's not a tangent line, but what you could do is you could pick some point up on the graph, and you can actually know the value of that point, and you can find the delta x of that point. You can find the delta y of that point, you can find the delta x of that point, and those could be just numbers, and you could actually calculate the slope of this chord. In fact, that's the only thing you can calculate. This is the only thing you can calculate. In order to have a slope of anything, you must have a delta y, you must have a rise, and you must have a run. Delta y divided by delta x, that's slope. That's what slope is. But so you could calculate it. Now, there's a problem. That the slope of this chord is not close to the slope of the tangent line. Notice here's the slope of the chord, but here's the slope of the tangent line. Notice those two slopes aren't very close. But here's where Isaac Newton shows his brilliance. He has this wonderful mathematical imagination, and you might have this also. Well, how could we make those two slopes, this slope, closer to this slope? And you might know where I'm going. This is exactly what Isaac Newton thinks. He says, what if the triangle were smaller? And notice that now with a smaller triangle, so what we do is we pick a point up on the curve a little closer to our initial point, notice the slope of this chord is now closer to the slope of this tangent line. And if the triangle was smaller still, notice that those two slopes are really pretty close. And actually I had trouble drawing the chord, but those two slopes are supposed to be pretty close. And for a really small triangle, notice that the chord, the slope that I can calculate, the one that goes with delta y over delta x, that slope looks really close to the slope of the tangent line. Here's how Isaac Newton's going to do this mathematically. He's going to start with an equation, but he's going to use function notation. The equation is going to be f of x equals x squared. This could just as easily be y equals x squared, but we're going to use function notation to emphasize the fact that there could be a lot of different variables besides x that we could have on the x-axis. So we could have f of t equals t squared if it were like an equation for time on the x-axis. But essentially you can think of f of x and y as the same thing. So what we're going to do is we're going to find the slope of the tangent line right at x equals 2. And how we're going to do this is we're going to imagine a variable x on the x-axis, and we're going to find the slope of the chord that goes between these two, our variable x and the point where we're going to actually find the tangent line right at x equals 2. And we're going to actually calculate the exact slope of the tangent line at x equals 2. But in order to do that, we have to use this sort of, we call it in calculus a dummy variable, because this variable we're going to use our imagination to change on the x-axis. So notice that here's the slope of the chord, and so this is the slope that we're actually now going to calculate using an equation. And you can tell that it's not very close to the tangent line. Right? But once again, in this case, we imagine a triangle smaller and smaller. And notice as x gets closer and closer to 2, those two, the slopes of the tangent line and the slope of that little triangle slope, they're getting closer and closer. The plan is to write an equation for the slope of this red line, and then imagine x getting closer and closer to 2, and therefore we would know that the slope of this red line would be closer and closer to the slope of the tangent line right at point 2. So remember, the slope of a line is rise over run, also known as delta y divided by delta x. So to write that on an equation, we have to calculate out what delta x is, and this part is easy. Delta x is just the change in x, which is x minus 2. So delta x is x minus 2. Delta y is a little bit harder, so we need to find the change in y values. So we need to find the change in y values, which means we have to know this y value over here and this y value over here. Since we know the equation f of x equals x squared, it's easy to find the y value. So we just go plug in 2 squared, well, that's got to be 4, and we're going to plug in x squared, well, that's x squared. So the change in y values are going to be x squared minus 4. So now we know the change in y, and we know the change in x, the delta y and delta x, that's also called the rise over the run. So, slope is the rise over run, also known as delta y over delta x, and in our case, our slope is x squared minus 4 divided by x minus 2. Now remember what the plan was. We're going to imagine x getting closer and closer to 2. Because as x gets closer and closer to 2, we can see that the slope that we're calculating on our little slope equals delta y over delta x equation gets closer and closer to the slope of the tangent line. Now, here's the problem, and you might see this coming. So this equation is the slope of that little triangle that we've been drawing. But really, what we want to get is the slope of the tangent line that we know that when x gets closer and closer to 2, this equation gets closer and closer to the tangent line, because what we really want to know is the exact slope of that tangent line, like so. Now, here's the problem. We want to know this equation is exactly like the slope of the tangent line, only when x is exactly equal to 2. So the problem is, as you know, if we put in x equals 2, we'll get slope equals, I guess I could draw this, x squared minus 4, that's okay, but 2 minus 2, that's a problem, because 2 minus 2 is 0, right? And there's something I have to tell you about dividing by 0, and you have to know what division means. Let's say you have 20 apples, and you divide the 20 apples into 5 groups. 20 divided by 5. The answer is going to be 4, because if you take 20 apples and you divide the 20 apples into 5 groups, each of the groups will have 4 apples in the group. That's what division means. So you have to take 20 apples divided by 5 means you have to separate the 20 apples into 5 groups. That's how you do division. So if you took 20 apples and you divided them up into 0 groups, what does that even mean? Right? It doesn't mean anything. Like it just doesn't. In math, that is nonsense. It's nonsense. Now, interestingly enough, just as an aside, it is possible to take 20 apples and divide it up into half a group. That's totally okay. If you know fractions, you know what happens then. But you just can't divide 20 apples into 0 groups. And when Isaac Newton saw this, he said, wait a second, the exact number I want right here gives me a divide by 0. I believe that other mathematicians got here and they just gave up. Like, I bet somebody thought of calculus before Isaac Newton, probably somebody thought of it before Leibniz. They got this far and they said, oh, I can calculate the slope exactly, except I'm going to divide by 0 right here. If I calculate the slope exactly, I'm going to have a divide by 0, and that's just anathema to all of mathematics. And other mathematicians who weren't Isaac Newton, they said, oh, that's just impossible. You can't divide by 0. And they just gave up. Isaac Newton, on the other hand, he gets this far and he says, no, I'm not giving up. I need to know the slope of that tangent line because I need to know the velocities of moving objects. And so he says, here's what I'm going to do. I'm not going to let it be a divide by 0. I'm going to make it be this. Now notice the top half of the equation, you can factor it. X squared minus 4 is the same as x plus 2 times x minus 2, right? And notice what happens if you factor the top. Look what happens. You can cancel out those equations. And what you get if you factor and cancel the top, you get the slope really equals x plus 2. Alright, so look at the trick that Isaac Newton pulled. He did get a divide by 0, but then he noticed, oh look, you can factor and cancel that top part. And when you factor and cancel that top part, you can get two parts of the equation, and the important part, this part, cancels out. It goes away. We no longer have a denominator. We have just slope equals x plus 2. And now we can totally put in x equals 2 into that equation. We can totally put in x equals 2 into that equation, and here, notice, what slope really is 4. And so Isaac Newton says, oh, you know, the slope of that tangent line, it's got to be 4. It's got to be 4. It has to be 4. And he says, I've invented calculus. The slope of that tangent line, right at x equals 2, that is 4. That is how calculus was invented. That's the big trick. The big trick to calculus, I got to tell you, it's kind of sad. Big trick to calculus: factoring. Factoring. You factor and you count and you cancel, and you get the slope of x equals 4. Now, nearly every mathematician in the world believes that's true. That's totally right. Calculus is true because factoring is true, canceling is true. But I want to tell you that there are certain philosophical problems, even though everybody really in the real world accepts that calculus is true. I want to just go off and tell you there's a little problem with this, and there's some tiny minority opinion that there's a dissent. There's a dissent to this. And I just want to tell you, if you're going to learn calculus, you should know there's also some objection to calculus, and here it is. Here it is. Differential calculus is based on the claim that this equation is equal to this equation. Now, this equation is sort of equal to this equation in the sense that if you factor out this top and you cancel, it becomes this equation. And in fact, for all intents and purposes, except for one little tiny exception, these equations are identical. Now here's the one little tiny exception. These two equations, and what I've done is I've made a graph of this equation and the graph of this equation, and notice that those two graphs are exactly identical graphs, except at x equals 2, this equation, this is our original equation for the slope in our little triangle, and this is our equation actually, we're going to say that this is when we put x equals 2, that's the slope of our tangent line, but the only time in the infinity of possible x's, the only time where this equation is not equal to that equation is only one single occurrence at x equals 2, where here we call that, and this equation is undefined at x equals 2, this equation is defined at x equals 2. And here's the objection to calculus. The only time these two equations are not equal is the specific x value for which we have to plug in x equals 2 to find the slope of the tangent line. Now, you can see where mathematically some mathematicians could have problems with that, right? The equations are everywhere equal except the exact value that we want to know the value of this equation. And what Isaac Newton's answer to that was pretty much, just ignore that. Don't worry about it. Don't worry about it. Just because x equals 2, the point that we want to know, we're changing this equation that has this undefined point right at x equals 2 into this equation that has no problem. Because we can't divide by 0, Isaac Newton just brushes that under the rug and he says, nope, don't worry about it. It's just okay. It's okay. He Jedi mind tricks all the other mathematicians into believing this. Actually, that's not true. Notice that a mathematician would not accept this claim that this equation is equal to this equation at x equals 2. That's just wrong. It's not right. These equations are equal for all values except for x equals 2. That's mathematically certain, right? The only reason why anybody believes that, now here's the thing, this problem is, the only reason that anybody believes this is because if you go out and you plot the actual speed of a car and the actual speed, and then you do this derivation, and right at x equals 2 seconds, you look at the speedometer and it matches your graph, the speedometer will actually say, oh, the speed right there at 2 seconds was in fact 4. Calculus has to be experimentally verified, otherwise no one would have believed it. Because of this. And it's kind of so here's one thing. If you're an engineer or if you're a physicist, what you think of this? Of course, it's been experimentally verified. If you actually do an experiment with changing velocity and you actually calculate the velocity right at x equals 2 seconds, you really do get 4. Calculus is true. But if your sense is, oh, that's disturbing. Something's wrong with that. Despite the fact that it's, if you do an experiment, it comes out, there's still a divide by zero. It still has this right at the place where we want to know, where the x value has to be 2, it's got to divide by 0. With that difference, I feel, is that means you're a mathematician. If this is somehow distasteful to you, this is painful to think about, that all of calculus is based on this kind of, I don't know, unattractive divide by 0, that's your mathematical, that's your sense of mathematical beauty, and you should cherish that. And calculus at its heart has this little bit of ugliness in it that I just feel that you should know about, and you should be able to hold an intelligent conversation about, because that's what it means to be a human being and know our culture in totality. Calculus is part of our culture.